Hello everyone! Today we're going to be talking about sound waves in an open closed tube, and we're going to annoy our roommate with some Coke bottle physics. My name's Olivia Jenks, and other members on this project are Amber Chavez, Rachel Felix, Simone Griffith, and Samantha Garcia. It is possible to create multiple standing waves in a tube as long as the open end has an antinode and the closed end has a node. We can describe which standing wave is present using the mode number. The mode number, denoted N, describes the number of half wavelengths present in the tube. Because open-closed tube systems have a node at one end and an antinode at the other, they only produce standing waves with an odd mode number. The different standing waves in the same tube are called harmonics. It is possible to calculate the wavelength and frequency of standing waves using the length of the tube. Remember that for an open-closed tube, the mode number must be odd. To find the wavelength from tube length, simply multiply the tube length by 4 and divide by the mode number. To find the frequency from the wavelength, divide the speed of the wave by the wavelength. Finally, to find the frequency of the wave using the tube length, multiply the mode number by the speed of the wave and then divide that by 4 times the length of the tube. The frequency of a harmonic can also be found by multiplying the mode number by the fundamental frequency, which has an n of 1. Now we get to have some fun. First, you're going to need to find a 355 milliliter or a 555 milliliter glass Coca-Cola bottle. You'll also need to have an audio spectrum analyzer app or any online sound analyzer. You'll need some water, a tape measure or ruler, and yourself. First, you're going to record the interior length of the bottle using a tape measure. Take an empty glass Coke bottle and rest the opened end of the rim on your bottom lip. Gently blow on the bottle until you hear a sound. Using your audio analyzer, determine what frequency you heard. If you tighten your embouchure and blow more forcefully across the rim of the bottle, you might be able to produce higher tones like the third and fifth harmonic. The next video will demonstrate the fifth, third, and first harmonic respectively for one tube length. Next, add a bit of water to the bottle and measure the interior length of the bottle from the top to the waterline using your tape measure. Then, repeat steps 3 through 5. You can keep altering the amount of water as much as you'd like to change the length of the tube. For each tube length and harmonic, you'll need to calculate the theoretical wavelength and frequency. Here are some sample calculations. For the third harmonic of a tube of length 0.255 meters, we found that the wavelength was 0.340 meters and the frequency was 1010 hertz. Next, we need to calculate the observed wavelength from the measured frequency. We found that if the frequency was 894 hertz, the wavelength was 0.384 meters. A sample of our results is shown on this slide. Please take the time to pause the video and see what we found. Of course, there's always some amount of error that comes from the application used to measure the frequency. However, that can't explain why the first harmonic was so inaccurate. It's possible that the lowest sound produced by the bottle was actually created by resonance of the glass instead of the air column inside the glass, and that the third and fifth resonance frequencies didn't have this anomaly. There are a few reasons why we think this could have happened. Qualitatively, when we thought we were blowing the first harmonic, we could feel the glass vibrating, meaning that there were some wave vibrations of the glass itself. Quantitatively, however, our percent error was often huge for the fundamental frequency, but often pretty accurate for the third and fifth harmonics. Thanks for listening, and go out there and thoroughly annoy your roommates in the name of physics.